So a buoyant force is a force that's produced when an object is submerged within a fluid. Now, this fluid could either be a liquid like water, or it could be a gas. Think of a helium balloon having a buoyant force because it is surrounded by a fluid or the air. Looking at buoyancy, we can understand buoyancy and how that force comes about based upon pressures. So if we think about an object that is submerged within a liquid, there are two pressures that we're going to focus on: the pressure of the water on the top, as well as the pressure on the water at the bottom. What we can say is that pressure 2 is greater than pressure 1 for the fact that pressure 2 has a greater depth. Right? If we remember that pressure is density times gravity times depth, right? Because pressure 1 is at a shallower depth and pressure 2 is at a deeper depth, pressure 2 is actually going to be slightly greater than pressure 1, just slightly depending upon the size of the object. So let's find the buoyant force then based upon our pressures and see how there is a net force upwards in this circumstance. If we know that from the equation for pressure, that force equals pressure times area, if we imagine an object which has an equal area on top and bottom, the force pushing down, force 1, would be pressure 1 times area 1, and the force pushing up would be pressure 2 times area 2. What we can then look at is the net force. The net force is going to be the force 2 pushing up minus F1 pushing down, and that's going to be what produces my buoyant force, or FB. So let's solve for F1 and F2 and see then how we can determine what FB is based on the physical characteristics of our situation. So looking at F1, F1 is pressure 1 times area 1, which means we can also write this as the density times gravity times the height 1 times area 1. That's pressure times area, and that's going to be the same for force 2. The only difference in my equation is that this is now going to be height 2 rather than height 1. And again, this would be height 1, this would be height 2. Now if we can plug that into this equation here, we'll see that the buoyant force is equal to force 2 minus force 1. And we see some things here that we can simplify this equation with. Some similarities is we have density times gravity, and then our areas are actually going to be the same as well. So we'll rewrite this as density, gravity, area, and then what we have is H2 minus H1. Well, looking at this, H2 minus H1 is actually going to be we'll call it capital H, or the height of my object. And then looking at this as well, I can see that if I take the area of the object times the height, that is the volume of my object that is submerged. So I can then simplify this equation in my equation for a buoyant force as force buoyant equals the density of the liquid or the fluid, so we'll say density of the fluid, times gravity, times the volume that is submerged. And that's how we're going to be able to calculate the buoyant force. When we talk about volume submerged, that's important to understand that it's not the entire volume of the object. What we have here are 3 objects that have different volumes that are actually submerged, and so it would just be this volume here that we would use in our calculation to calculate the buoyant force, whereas this volume here, and then this is my complete volume of the object that is completely submerged. So understanding that in terms of the buoyant force on all 3 of these objects, this would have a buoyant force there, this one would have a larger buoyant force, and this one would have the largest in terms of this has the greatest volume submerged, the second greatest, and the least. Their density of the fluid is exactly the same because they're in the same fluid, and gravity is going to be the same. So the size of the buoyant force is going to be really dependent upon what liquid we're in, as well as how much of the object is actually underneath the surface of the water. The last thing we're going to talk about with buoyancy is the idea of Archimedes Principle. What that talks about is that when an object is submerged in a fluid, that fluid is displaced. So if we have a 10 meter cubed container and we submerge an object in it, some of that water is going to overflow. And so let's say 2 meters cubed of that water actually overflows in this circumstance. What we can know is that the buoyant force, which is going to act on this object, is going to be equal to the weight of the water that was actually displaced. So in this circumstance, there's actually 3 forces that are at play. One is the force of gravity, pointing down. A second is a buoyant force, pushing up. And a third would be a normal force, because it is resting on the bottom of the container. And just like when we have a book sitting on a table, there's a normal force. In this circumstance, the net force on our object is going to be the force of gravity In this circumstance, our net force would look like the buoyant force plus the normal force minus my gravitational force equals mass times acceleration. Because our object is stationary at the bottom, we know that acceleration goes to 0. And so what we can say is that the buoyant force minus my normal force is going to equal my force of gravity. But how could we determine the buoyant force if we don't necessarily know the size of our object? But we do know that the 2 meters cubed of water overflowed when the object was submerged. So what we can say is that the buoyant force equals the weight of the water. Remember, weight is just mass times gravity. And if I don't know my mass, but I know my volume, I can say that that is also volume times density times gravity. So the volume that was submerged, or the volume that overflowed, times the density of the liquid times gravity, and you'll notice that looks very similar to our equation that we had for buoyant force in the first place. The reason that this works is because the volume that this object is here is going to be the same as the amount of water that overflowed from my container. So that's why we can say that the weight of the liquid that is displaced is going to equal my buoyant force in this circumstance, because the math shows that it's the exact same thing.